Swayam Prabha. Digital India. Educated India.
Yeah, so we will start off with a new idea of availability. And this is probably one of the last major idea that we'll see in this course. And of course, we have seen that what we mean by irreversibility. We have seen that there is irreversibility is like lost work, and work is lost in cases, or if the processes are irreversible, then some work is going to be lost, and that is related to the irreversibility, which is there in the system. Now, the idea of availability is something which is new, relatively new. Of course, it is going to be related to the idea of entropy that we have been talking about earlier. So let me just introduce the idea of what do we mean by available energy? So let us say that there is a heat source at temperature T, and we are asking the question, what is the maximum work that can be produced using this heat source? So of course, when we want to convert heat into work, we think of a Carnot engine, and an ideal Carnot engine is the most efficient heat engine that we can have. We have already shown that any other engine cannot have efficiency which is greater than the Carnot engine. If the engine is reversible, then it will have the same efficiency. If the engine is irreversible, then it will have a lower efficiency. But in no case can the efficiency exceed that of a Carnot engine. So the work done is of course QH minus QL for a Carnot engine. And if we were to represent these processes that are happening on a TS diagram, so you can say that this temperature TH or T here is the temperature at which heat is available. And this is the lower temperature at which the heat has to be rejected by a Carnot engine. So you can see that this part of the energy, so you can see that this total amount of energy which was available at this temperature TH is all this area, the two rectangles taken together. But because you have to reject heat at a certain temperature, which is like your ambient temperature T naught, you cannot avail this part of the energy. Okay, so that's where the term available energy is coming to the picture, and this idea of availability comes into the picture. So what we are saying is that all this energy that we have in this heat source is not available to us to convert into work. Only a certain fraction can be converted, and the remaining has to be just thrown off. And what needs to be thrown off can be given in terms of T naught and delta S. So it is very obvious here that T naught is of course the lower temperature, and delta S is of course the change in entropy, S3 minus S4. That is what is leading to this loss of energy that would happen. So now what is getting introduced here is that the idea of environmental temperature. So you can see that we are going to operate a Carnot engine, which is, let us say that the heat source is at 1000 degrees Celsius. So between 1000 degrees Celsius and my room temperature or my environment temperature, which is, let us say 25 degrees Celsius. So I can only avail energy till 25 degrees Celsius. So you will see that this environment temperature now starts becoming very important, and we will see that it will start showing up everywhere. And that's why we have written this QL in terms of T naught and delta S, because we would like to emphasize the importance of T naught here. Of course, this means that if you can lower your ambient temperature and you can do your things, then of course the amount of energy which you would have can be increased. Okay, but of course the you have to ultimately work with the atmospheric temperature that you would have. So you cannot, and you do not have a whole lot of leeway there. You cannot go to, for example, 4 Kelvin and say that I'm going to work, or 0 Kelvin and say I'm going to work with that. So because that is not going to be practically possible. So you'll have to, so the temperature that you have is what you'll have to work with. So of course, this clearly gives us the fact that not all energy which is available can be converted into useful work. So we'll start seeing this. So in some sense, you can say that I'm not doing anything new. I always knew, or from the previous ideas that we have discussed, we have already seen that a Carnot engine or any engine has to reject heat. Only then it can complete the cycle. So now we are saying that this QL is nothing but can be related to the environmental temperature. So that is the sort of the new thing that we are bringing in. Of course, not all energy is available. That is sort of known to us now from this idea. And we can see that the important role that the environmental temperature is going to bring in is what comes into the picture. And of course, that helps to define what is the available energy that we would have, or that is available to us from this heat source, which is at a certain temperature. So now let us look at an important idea, and we'll see that we are interested in doing a similar analysis. So there in the first case, we said that there is a heat source at a certain temperature and how much heat can be extracted from there. Now let us say that there is a control volume. Of course, control volume, we know there is some mass entering, some mass leaving, there could be multiple streams. Uh, and we would like to know how much work can be extracted from processes going on in this control volume. So that's a basic question that we're asking. So just like in the previous case, so here we are now sort of extending this analysis or this idea to the idea of a control volume. And however, our question remains the same. How much work can be extracted from processes from this control volume? So we will try to answer this. And let me tell you, this is one topic where I have spent hours and hours of preparing these few slides. Because if you look at various sources, they just give you so many different confusing things. So what we will do is we will start off with a relatively simple case, and then once with this case is understood, then we are just going to say that if we were to generalize this, then this is what we would get. So you see, all the complexities are going to be there in this case, but not unnecessarily complexities which could confuse us. So we will take the case of a uniform state process which has a single entry and a single exit, and negligible changes in kinetic energy and potential energy are going on. So if you would recall, we would always have two sort of idealized or simplifications. One is a steady state and the other one is a uniform state. And in this case, we are bringing in the uniform state process assumption. And of course, we are going with a single entry and a single exit. So this is my control volume. And in this control volume, there is some mass Mi which is coming in. There is some mass Me which is leaving. And as we know by now, the enthalpies, the what energy comes in is of course MiHi. Of course, you could have brought in the kinetic energy and the potential energy components, which we are neglecting or which we are not considering for now. Now, again, this question arises. Certain people ask, why not Ui? Why Hi? Okay, why not internal energy? Why are we considering enthalpy here? And then you would recall that when we have to, this mass has to enter, it has to do work again because there is a certain amount of pressure here. This mass needs to enter this control volume, and for which the flow work, some work also needs to be done. So that's a PV work, and that gets added to your internal energy, and that's what becomes my enthalpy. Okay, and if you're not clear, you can go back to the derivation that we had done when we were introducing our first law for a control volume. So the bottom line is then when we have flow in and flow going out, then the enthalpies get involved. And when it's a control uniform mass, there is no mass exchange which is happening. It's a closed system. Then the internal energies will get involved. Okay, now in this, so we have already assumed single entry and single exit. So there is only one MIHI, there is only one MEHE here for this case for now. We will generalize towards the end. Now, of course, in general, there could be some heat addition that could happen to this control volume, and there could be some work which is being extracted from this control volume, which are given as QCV and WCV. And right now we are saying that things can be irreversible in this control volume. So what we are going to consider now, what the question that we are asking is, of course, is, how much maximum work can we extract from this control volume? Okay, and that's what we would call that in the title here is the reversible work that is available for this control volume. Now, what will we do? How will we find what is the maximum work that is possible? Of course, maximum work is going to be possible when all processes, everything inside the control volume is reversible. Okay, so we are now saying that instead of considering this is what is actually happening. But what we would like to do is consider the case because we're interested in what is the maximum work that is possible. So I will now look at a case where things are almost the same. Of course, they will not exactly be the same. I will tell you what is same and what is not the same between the two cases. But what we are substituting is that whatever is happening inside this control volume, which was irreversible, friction and other types of irreversibilities were there. Now we are saying that those are not there. So that is the basic difference in the two control volumes. But the mass which is coming in, the mass which is going out is the same. The amount of heat which has been added is the same. Okay, the only difference is now the amount of work that I can extract from this control volume is different. Okay, so you can see that QCV, MIHI, and MEHE are the same. Now we have to remember that how do I make this processes everything reversible. So here the temperature of the environment is some T naught, the temperature of the control volume is some T. They are not the same. So how do I connect? How do I bridge this?
We need to make the temperature difference infinitesimal.
Yeah, but these two things are given to me, no? My T is given and T naught is given. So we had talked about, remember this example that we had talked about? So this is the same example now. So we were condensing water, which was at 100 degrees Celsius, and the environment was at 25 degrees Celsius, right? Or in this case, it was heating and at 100 degrees Celsius. And we said that if only we could heat it at 100 degrees Celsius, then there would be no net change in entropy that would happen. Okay, now to do that, we said that we need to connect a Carnot engine, which will take in heat from the environment at 25 degrees Celsius. We do some work on this Carnot engine, and then it will supply heat at 100 degrees Celsius. Correct? So then there will be no difference in the temperature of the system and the surrounding. Okay, and of course that would be reversible. So then this heat addition process would become reversible. Okay, so the same thing we are doing here now. Same thing is going on here. So we have connected a heat engine, and this heat engine is what is taking in heat and giving heating this control uh, volume so that everything here, the heat addition also becomes reversible. So you can see what we are saying is inside this, processes are reversible. The way the heat is getting added, everything is reversible there. and therefore the amount of work that I would get will be the maximum, which will be this arrow here, which I have not written, which will be the sum of these two. Uh, I mean, in fact, it should be the other way around. There will be some amount of um, work that I need to supply here. But so that is what the two works. I mean, so the work which is coming out of this control volume is now given as WCV reversible. Now, otherwise, the mass flow rates and the heat which has been added are the same between the two scenarios. So I'm now going to write out the first law and the second law for control volume. Okay, and of course, second law is for a reversible process. So these are our equations. We have already assumed single entry, single exit. We have already assumed that this is a uniform state process. So for a uniform state process, this is the equation. I have just taken it from the earlier things. For example, I think you see here. Yeah, so this is the equation that we have just taken. Just copied and pasted here. And similarly, this equation is exactly the same as a uniform state process, which we had introduced or which we had seen in the previous class. So these are the equations applicable for a uniform state process. Now we are going to apply it to this control volume. And in this control volume, we get rid of the summation sign. We change Q to QCV, and WCV to WCV are reversible. I mean, this is as per the notation that we are using for this control volume. And if we were to write out the second law will give us this equation here, where again we have gotten rid of the two summation signs. And of course, we have put the lost work as 0 because everything is reversible. And of course, we have just said, for the sake of simplification, although this was not really required, but I have just made the simplification that QCV we have integrated it, QCV dot we have integrated it, and we have gotten this QCV. Now we are going to write out an equation for the Carnot engine as well. Now for the Carnot engine, we can write out that the work that we get is, of course, Q naught minus QCV, and I get the second relationship, which is, of course, you can put it with the reverse sign. So the other relationship that we get is Q naught upon T naught is QCV upon T. Now, where is this relationship coming from?
Temperature scales.
Sorry?
Is that coming from the temperature scales that were defined?
Yeah, so this is how the temperatures were defined. That's right. So this is the based on the definition of absolute temperatures, we write this relationship here. So from these two relationships, so what we have done is we are analyzing this system, our control volume, we are analyzing our Carnot engine. We have all the equations that we need, and then we will start essentially eliminating the terms that we're not in, quantities that we're not interested in. So to begin with, we can eliminate our Q naught from these two equations. And I get the WC is equal to this term here, which of course I can rewrite as this equation here. So I will go a little bit fast here because the derivation this is all derivation, and I have already given the exact steps in these slides. So next I can eliminate QCV upon T. So QCV upon T is appearing in this equation as well as the previous equation. QCV by T is appearing here. Okay, so I eliminate this equation, QCV by T, from the entropy equation. Okay, by using this expression, and I get this expression here. which of course I'm just rewriting in this form here. And finally, I can eliminate QCV using the energy equation. So you can see that right now, first we started off with the Carnot engine equations. I wrote all this. Okay, I got QCV by T. Now I'm bringing in the equation. I have two equations for the control volume as well. First law and the second law. Now we are using the second law equation first, eliminating QCV by T first. Okay, so I get this relationship here or this relationship here. And then I'm eliminating QCV. QCV is still appearing in my first law. I'm eliminating QCV finally, and I get this relationship here. Okay, so you can get this work done as this term here, or if you were to eliminate WC, this involves WC. If you were to eliminate WC and retain QCV, then this is what you would get as the expression. Okay, let me just pause and see if there is any questions regarding what we are doing or how we are doing it. Of course, the algebra, you can go back and just check this. I'm quite sure that there is no mistake. Of course, if there is a mistake, do let me know and I will correct that. Is the idea clear and how we are proceeding clear?
Excuse me, sir.
Yeah.
Sir, if heat is rejected in from the Carnot engine or in this process, the maximum work that we can get is certainly less than WCV, right?
Yes. Now, WCV is what is being produced by this control volume.
Okay.
Okay, so I will essentially look at WCV reversible. Of course, there is some work which is going to be gone here if you were to work it like this. So we have written out expression for both the cases. If we were to write it out for WCV plus WC, okay, or if we were to write it out for just WCV in terms of QCV which has been added. So you can check the algebra. That is again, as I'm saying, I'm quite sure it is error free.
Excuse me, sir.
Yeah.
Sir, in the irreversible one also, it is we are adding QCV only. So in the reversible one, why did we have to like take Q naught and pass it through a heat engine and then supply QCV if there is already QCV available for the irreversible one?
Yeah, so I added this heat engine just to sort of tell you that how can we make this process reversible, everything. So now you can see that everything in this situation has become reversible. Okay, because we are adding heat to this reversible heat engine. And of course, we are saying that everything here inside this control volume is reversible. So everything here is now reversible. This entire thing is now a reversible process that is being taken together. So if you were to take this control volume and the heat addition process together, also everything is looking reversible now.
But had we only added QCV to the reversible control volume, then that would have also been like completely reversible, right? Without the heat engine, I mean, like just adding QCV as
No,
we
so
have
what
done
we
in the
do is that in
irreversible.
that case, because the temperatures are different here, you cannot add heat directly. And then again, going back to the example that I showed you. So if you are adding heat at 110 degrees Celsius, okay, so this is an example that we had seen earlier. If you're adding heat at, let us say, 110 degrees Celsius, then the change in entropy is not, net change in entropy is not zero. It turns out to be positive. Okay, so if we were to make this as zero, then you have to add heat at 100 degrees Celsius, and only then this entire thing becomes, the heat addition becomes not entropy generating process.
So are both the QCVs different, like for the irreversible one and the reversible one?
Uh, Actually, this is something, I mean, right now I'm thinking that they should be the same.
But if they are the same, then like in the reversible process, we are supplying heat at the exact temperature at which entropy will be zero. But
Right.
if we are able to do the same in the irreversible process, like supplying the same heat, QCV,
Mm-hmm.
then we don't need the heat engine in the
Yeah, I mean,
irreversible
okay,
one.
fine. If you don't like the heat engine, I'm sure you can do the analysis without the heat engine. Okay, but why I showed you, because I just wanted to make everything reversible here. Okay,
Okay, sir.
okay, so that was just the idea. Of course, the other things do not change, and maybe you can eliminate this heat engine and you can still get the same result here. That I have not checked, but maybe, I mean, I think that should still be possible. Okay,
Okay,
but
sir.
the basic idea of my adding the heat engine is to show that how to make everything reversible here, completely reversible.
Yes, sir. Got it.
And what actually that allows you to do, I think the most important relationship that you need to write here is this relationship here. Okay, you cannot write this relationship without realizing that there is a heat engine that you could connect. Okay, and this becomes important later on. I think that's where, so you cannot write out this term without writing this term here. So essentially you are using this relationship here in order to write QCV in this form. Otherwise you'll be left with Q naughts somehow. Okay, so as I'm saying, this is turns out to be a very confusing thing in various books if you look at. So I've tried to simplify it, and hopefully this is not confusing. So basically we'll understand how the modeling is being done here, and how and of course how we are writing down the equations. And then of course after that is once we have written the equation, or once we have understood the system and we have written the equations, then of course after that is just algebra that remains. So in this case, if we were to eliminate this term here, of course you have a direct relationship between WCV reversible and WC WC and QCV. This is, now you can use this relationship here, and you can write out WCV reversible as this term here, as all these terms here. So what the bottom line is that this is the expression, this is the maximum work, or this is the reversible work that you can extract from this control volume. Okay, and what is surprising here is that you again see your T naught, and I think that's where the heat engine, bringing the heat engine becomes important here, because if you don't bring in the heat engine, then it becomes very difficult to see why or how this T naught is entering into the picture. Okay, and this is T naught is essentially coming into the picture because once you see the importance of the heat engine. Okay. So now what we have done is, of course, written out this term, and we have deliberately put it in 3 lines because we would like to now, because this is now a reasonably complex relationship that we have, and we would like to interpret it physically. So we can see that the work term that we are getting is because of, this is a contribution of heat addition that I'm having. The second terms you can see are because of mass entering, leaving. Okay, so this is a contribution from flow terms that I can have. And now what are these terms? This is the change in the entropy of the control volume, or this is the change in the internal energy of the control volume. Okay, this is now my storage terms. I'm storing things, accumulating things. Okay, this is my accumulation term. Okay, so this is, so if you want to think of it, of course you can just, this is my mathematical expression and you can be happy with that. But if you are trying to think of this physically as to what is happening and what is coming, what is contributing to this work, so you can see that there are contributions from heat addition, there will be contributions from flow terms, and there is contribution from storage terms. And of course one or more of them can be zero, but in general, let us say all these of them are present. So then this is the expression that I would get for work done. So now what is the relationship between what we had earlier and what we have now? Is we can define that there is an irreversibility that we have. The work done that would come from my actual volume, and whatever is the work done, which is there from my other control volume. So the difference of these two we have already defined as irreversibility. And of course, now I have to tell you what is the work done from the control volume. So this is the work which is there, work done by the control volume. I can write it out like this. And then I can subtract out. So this work done is what is there. I'm just writing out. So this expression I already have. This is the expression that I have now found. And I can write out the irreversibility as the difference of these two terms. And this is the expression that I get for the irreversibility. Okay, certain terms will cancel out, but a lot of these terms will still stay. Okay, so this is after cancelling out the common terms. This is the expression for irreversibility that I would have. Okay, so now what we will do. Okay, any questions here again? So once this idea is clear that what we are trying to do is essentially change my reversible processes into an irreversible process into a reversible processes, and see what is the maximum work that can be extracted. And then of course the difference of these two is my irreversibility or the lost work. Okay, so we find out for both the cases and we look at the difference, and then that gives me the amount of the irreversibility that I have in my system on my control volume. And I now explicitly have an expression for that now. So now we can generalize this. So once we have understood this, and we have understood that there is going to be a contribution from each of these terms, heat addition, uh, the flow work, and the storage terms. So these terms have to be there. So now we are going to generalize that and say that this is the expression that we would have. So you can see that it is essentially following from the previous expression. Now the dots have been put in here. You remember that when we are taking a uniform state process, then we integrate it with respect to time, and of course the dots go away. Okay, so now the dots have to be put back. That is not a, that is one small change, but otherwise you can see that the form of the expression is exactly the same. Now the other difference that you see is multiplication sign, sorry, the addition sign I have put in, the sigma I have put in, because explicitly accounting for that the heat addition can be at different temperatures. So instead of having one heat source, you could have multiple heat sources, and the heat addition is happening at different TJs. Then I could repeat the whole exercise and get, so instead of this expression, I would get um, Q is being added at different temperature Tj. And of course, I will have to add it up in this manner here. Otherwise, it has the same form as whatever is happening. And of course, from the entropy generation point of view, this turns out to be important. And that's why we essentially write it out in this manner here. Now going to the second term, the multiple entry, multiple exit, that is quite straightforward. We have already seen that generalization by now, several times by now. All we have done here is essentially put the summation signs. We have collected our MIs together and MEs together. And if you do that, then this is what you would get. And then it's just that the summation has been added on top of that. Okay, so this is a straightforward term. Now, if you were to look at the storage term, instead of writing it out as, so this is nothing but S2 minus S1. Okay, capital S2 minus capital S1. And this is nothing but capital U2 minus capital U1. And of course, in general, it would be, because again, this has been integrated with time. So this essentially becomes ds dt for the control volume, the change in the total entropy of the control volume, and similarly the change in the total energy of the. Okay, so again, so this is where the steady state assumption, uniform state assumption we had used. And we are now relaxing that, and we are saying that this is the term that we would get. So the good thing from doing the derivation in this manner here is that it readily allows you to see how, I mean, it has enough complexities that you can see how the generalization would happen without having to deal with the complexity to begin with. Okay, so each of these terms can be very easily generalized, and or you can see how each of these terms could be generalized, and in general you can see that this is the expression I should have. And the dot, so the basic differences, of course, in which may not be very clear, is the dots which are there appearing in each of these terms. So of course the irreversibility finally can be given in a manner like this. Okay, of course, again, note the dot. So we have essentially introduced the idea of reversibility, or how to get reversible work from a control volume. We have written down an expression for that. And based on that, we could find out what is my irreversibility. So what we will do is we'll take a, okay, so I hope you can see the slides again. And so we have essentially looked at this idea of uh, reversible work from a control volume and the idea of irreversibility that we would have. Now we will go
Sir,
ahead. Yeah.
I have a doubt in that transition from uniform case to a general case. In the uniform case, all the space-dependent terms would have been neglected while doing that. So how are we accounting them in the general case? And how do we know that these terms were present?
Yeah. So basically, we are saying that. So I think you are confused about the first term here, or which term are you looking at? The last term, because the flow term is not an issue. Either the first term or the third term would be an issue. That is what I would imagine. Okay, let me just explain this again. The second term is the flow work term. So that is just me times T naught SC minus HE. That's what you would get here. And similarly for MI. Okay, so that's what we have here. Me HE minus T naught SC. And of course, all we have done is put a dot there and put a summation in here. Okay, so that is there for both the terms. So that takes care of multiple entry, multiple exit. Now, if I were to look at the storage term, this is capital S2, this is capital S1, and this is S2 minus S1 of the control volume. And of course, if you were to do it per unit time, then this is going to be dsdt. And similarly, the second term will be dedt. So these terms are also straightforward to see in some sense. I can generalize that. Now, the heat addition, let us say that this is happening at, so let us say that instead of having just one heat source here, I have another heat source which is here. So the flue comes in at a certain temperature, then it gets heated up with this because of this heating, and then there is another source of heating which is adding heat at a different temperature, and then it goes out. So for that, we are saying then, of course, we would write out this term for the first heat source, where this T corresponds to this heat source, and then there would be another one for the other heat source, and so on if there are multiple sources. So that's how we are writing out this term, Tj and Qj. Both of them should have the same subscript. Okay, that's what we mean here. That's the commonality between these two terms. So it's one Q1 and T1 at T1, Q2 at T2. Essentially, that's what we mean here. QCV at 1 happening at temperature T1, QCV2 happening at temperature T2, and so on. So that's what is writing here. We have explicitly, we have dropped this QCV, we have dropped, otherwise J terms we are carrying forward. And you can think of that this is the integration over J. Just like this is an integration over the inlet port, this is an integration, sorry, summation over the inlet port, this is summation over the exit port, this is a summation over all the heat sources that we have at different temperatures. So it's a summation over J that is implied here. Okay, I don't know whether there's any doubt which still persists now. Anything which still needs to be clarified here?
This would be valid if we are going from the uniform case to the general case and assuming that all those terms we are having in the uniform case are mutually exclusive, and hence there would be exact analogy for in the general case. But if in the general case there were other terms too which have a space variation, then while going from general to uniform we might have neglected or equated them to zero.
Yeah.
So
So,
how can we claim that those terms won't be there in this case?
yeah, no, your point is right. Okay, so your point is right that it is. So of course we are generalizing, and then whenever we generalize, we have to be careful. So your point is well taken. I'm not denying that. Okay, but what we are saying is that if I were to drive this equation directly, it is very confusing. Okay, with lot of, I mean, you can say that you have multiple sources, multiple heat, multiple sources, and all of them. Uh, I mean, and then you have to go. Everything is generalized, so it just becomes very messy. There is no point in going to that sort of an equation. So what we have done is taken a situation which is reasonably complex, and we know that the complexities from there will there are no additional complexities, so we are essentially taking care of all the complexities and not unnecessarily complicating the things also. So we will move ahead and say that, so we have seen what is the maximum work that we could get. Now the question is, if you are interested in how much maximum work we could actually extract, we have to also look at what is the final state that we could get to. So if this final state, what is the final state which will give me the maximum reversible work? Okay, so that together will constitute what is my availability. You understand? Earlier we were asking the question, what is the maximum work if everything was reversible? Now we are also saying that I can get maximum work not just by stopping in between, but if I could continue with that process to the point that I can go. So that will give me the maximum. Everything before that, I mean, here, whatever we had said earlier is we could stop in between as well. There is no restriction we are putting in. Okay, so this is going from T naught, Tj to T naught. Okay, but now what we are saying is the maximum work that we could get is we could not change our state any further. And therefore, that is going to be the absolute maximum that I could get in terms of the work that I can extract from my system. So now we are going to define what is the final state that we could have, and we are saying that the final state that we could have is that when it comes in equilibrium with the surrounding. Okay, so we are now looking at, again you can see that the surrounding is coming to the picture. Okay, the surrounding, we cannot get anything more than if the temperature, so now what we mean by equilibrium is that, I mean, we are saying that maximum work, the final state would be when the system is now in equilibrium with the surrounding. And what we mean by that, equilibrium implies that system is at the surrounding pressure, temperature, chemical composition, zero velocity, and minimum potential energy. Okay, so we are now minimizing everything, and we are saying that nothing else is possible now. Okay, it's the same. So if the pressure was, let us say I'm at a higher pressure, then of course I still have a tendency, I can still do certain work by expanding the gas, for example. Okay, but if I bring it down to the final pressure of the surrounding, then of course I cannot, there is no more work potential that I have. Similarly for temperature, and of course I could have chemical composition, which we are not explicitly considering, but we are making a note that I could have changed my chemical composition. But if the chemical composition cannot be changed any further, then of course I am in equilibrium, and of course with zero velocity and minimum potential energy. Potential energy is not zero, but it is minimum potential energy depending on whatever reference frame we are using to measure the potential energy. In that reference frame is a minimum. So, of course, then the maximum reversible work will be done by the system. And then we are now defining this availability is the potential to achieve this maximum possible work. Okay, so I think this is where we will leave you for today. So we have seen that what we mean by maximum work, maximum energy, which is available. This is what we saw here. And then we are saying that this gives us a very clear idea that the total energy that we have in my source, all of that is not available. Similarly, all my energy which is available in my control volume is not available for conversion into work. Okay, so this is what the two scenarios is giving us. And then we are finally defining that the maximum that I can get, which we are defining as the availability, is that when the system comes into equilibrium with the surrounding, and that is the maximum work that I could extract from it. Okay, and all these two things, these two ideas now are straightforward. The first idea was relatively complex, how to get this irreversibility at the amount of irreversibility that I have in the system, and how to get the maximum reversible work from a system. Those were the relatively difficult ideas, and then now it will be a easier ride from here onwards. Okay, so today's lecture was conceptually, there are a lot of concepts involved. So go back and look at it before you come back to the Thursday's class. And once you are clear about these ideas, again, we can clear any doubts in the beginning. Then once we are clear about these ideas, you will see that further things are very straightforward.